So I have a timer here, so hopefully I will have enough time, I will leave enough time also for questions, of which there will be plenty, I hope. So as Laszlo already mentioned, my group is working on experiments. We are working on mostly scanning tunneling microscopy and spectroscopy, optical spectroscopy of 2D materials, and also topological materials. And today I would like to introduce you to a very new and very exciting member of the ever-growing 2D materials family, which is platinum mercury selenide, which we have shown with STM measurements that it shows signs of being a very large gap K-milli insulator. So basically a heavy metal version of graphene. But first, let me just try to introduce you to why is it desirable and why do we want to work with materials that are 2D and that are topological. So let's just start with theory. This is a very recent, recent 2 years ago, the group of Nicola Mazzari has shown that if you do a large-scale computational study of available crystal structures, you will find that of the order of 1,000 materials are available for exfoliation and for experiments with these 2D materials that can be thinned down possibly to the monolayer. So we are talking about an order of 1,000 materials. And you get all different kinds of materials in this zoo. You get, as you know, graphene, which is semi-metal. You get insulators, superconductors, charge density wave materials. Recently, there's been a lot of work on magnetic insulators. And of course, you also get topological materials. And it's not surprising that you get topological materials in this 2D material family, because another recent large-scale theoretical study has shown that, again, doing very large-scale DFT calculations on available crystal structures, these guys that I've listed here have shown that around, well, almost a third of all available materials are potentially topological. So their band structures carry some sort of topological property. And with this, of course, there is surely an overlap between these van der Waals 2D materials and topological materials. And we are working on this intersection of the two, where you can get very interesting, very interesting physics and, possibly also very interesting applications. So basically, the real power of 2D materials is, first of all, lies in the fact that there is this whole zoo of them with very different properties. But it could be argued that an even larger advantage of these materials is that you can kind of use them as Lego bricks, as André Geim has introduced, that you can stack one on top of each other, and you can do this stacking in a way where you can achieve configurations of 2D materials which are basically not available through any other means. So you can't grow, or it's very hard to grow materials on top of each other sometimes. And you can make stacks of these 2D materials and atomic configurations which are basically not available through a thermodynamic path. And one of the most interesting and simplest examples of this is this, of course, this magic angle graphene that we've heard at the talk of Pablo Herrero in the beginning of this conference. Also, you can do this very twisting, this bistronics kind of thing with transition metal dichalcogenides. So this is just a snapshot of some new results from my group, where we've shown that you indeed also get these flat bands in twisted molybdenum disulfide bilayers. So this physics is ubiquitous basically in the TMDCS as well. But if you turn to topological materials, you can also do this kind of stacking if you have 2D topological materials. And I've just picked out this one example to show you the power of this kind of stacking and this playing around with these materials, like with Lego blocks. And this is a very nice experiment from the group of Benjamin Hunt in the US, where they placed tungsten ditelluride on top of niobium selenide. And some of you may know that niobium selenide is a superconductor, and tungsten ditelluride is a 2D topological insulator. So what you can do is, through the proximity effect, you can induce superconductivity in the edge channels of this tungsten ditelluride. And it just takes one small leap of the imagination to go further with this kind of physics and this kind of building with Lego blocks. You just need a small Zeeman gap, possibly maybe through combination with a ferromagnetic insulator, and already you could play around with Majorana physics in this system. So basically, this whole business of 2D materials was started with graphene, and with the discovery of the half-integer quantum Hall effect in graphene. But graphene is also intertwined quite deeply with the evolution of the field of topological insulators. I'm sure most of you know these famous papers by Kane and Mealy, where they've shown that graphene is indeed the prototypical two-dimensional topological insulator, or as sometimes it's called, is the quantum spin Hall system. So they have shown that if you switch on spin-orbit interaction, then the graphene band structure gets gapped, and you get these spin-polarized edge states, which are protected by time reversal symmetry. Problem in this case is that in the case of graphene, due to the very small spin-orbit coupling of carbon, you get a band gap of the micro EV range. So what we're basically looking for is, if we want to explore 2D topological insulators, is some kind of heavy metal version of graphene, if you don't mind the pun. So while we're looking for this heavy metal graphene, it's maybe worth to kind of formulate a wish list, as you wish, for the properties of a 2D topological insulator or 2D quantum spin Hall system. Well, it should have, of course, a large band gap, as we discussed. So the larger the band gap, the easier it is to integrate into any practical application. It should be possible to exfoliate. So just like graphene, it should be easy to exfoliate. And preferably, it should be stable under ambient conditions. So this is, I think, a very important consideration. Just think of the situation where if graphene was not a material that was stable under normal laboratory conditions, you would need, for example, UHV to handle it, or it would need some other exotic lab environment for you to be working with it. So the literature and the field would not have exploded in such a way as it did. So this requirement kind of makes the material available for a lot of different labs and available for a lot of experiments. And as I will hopefully show you, this material, this platinum mercury selenide, is a material that fits this wish list quite well. But first, let's take a small detour and look at what kind of materials we are talking about. Let's focus in on what's the state of the art of this, looking for heavy metal graphene versions and 2D topological insulators in general. So if you want to make a heavy metal version of graphene, well, first, the most obvious thing is to look at these carbon group elements, these group 4-ins, as I've called them here. So silicene, germanine, stannine, plumbine, and as you go deeper and deeper, or further down in the periodic table, the spin-orbit coupling increases, and you would get a larger and larger topological band gap. And indeed, I'm showing here an example of stannine. This has been produced using molecular beam epitaxy, and people have shown with STM that, sorry, indeed this material hosts edge states. Another prominent example, and possibly the largest bandgap material that you can get, is a monolayer or a 111 bilayer of bismuth, which should have a band gap in the hundreds of milli-electron volts, so well above room temperature. And this recent experiments have shown that something very similar can be grown on top of silicon carbide. So this is not purely a 111 bilayer of bismuth, but it's a combination, or it's a chemical compound basically between the silicon carbide surface and the bismuth, where the bismuth forms these honeycomb lattice, and the gap that was measured from STM is of the order of 0.8 electron volts, so very, very large. In these cases, in these two cases, and most others that I have not mentioned here, so for stannine and for this bismuthene, the structure of these materials, so the crystal structure is intrinsically linked to that of the surface. So these materials do not exist without the surface on top of which they are grown on. So, or it would be very hard to remove them. So this is a no-go area from an experimental point of view. So these are not, well, they are 2D materials, but they don't have the flexibility of self-supported 2D materials. So we should look to van der Waals 2D materials. The main motivation here is, again, is just doing experiments in a simple way. So for mercury telluride, you know, the prototypical quantum spin Hall system, or this bismuthene and stannine, you need very elaborate UHV molecular beam epitaxy systems to make these. So the accessibility is not very good for a lot of experimental work groups. On the other hand, working with van der Waals materials, well, you could jokingly say that all you need is just some Scotch tape and you're done. So the most prominent van der Waals topological insulator family would be probably the 1T prime mode or variant of the transition metal dichalcogenide, so molybdenum sulfide, selenide, tungsten sulfide selenide, and so on. And it's been this very good paper in Science, this theory paper, which actually showed that all of them are quantum spin Hall systems if they are in this 1T prime state, which I mentioned is a metastable state for most of them, with the exception of tungsten telluride. And indeed, in the case of tungsten telluride, it has been shown by STM and also transport measurements now that it is indeed, it is almost for sure that this is a topological insulator with protected edge states. And it has a host of other interesting properties, which I will not go into at the moment. Another part of this family that I have to mention is probably not so well known, but it's this bismuth rhodium iodide. This was actually the first weak topological insulator to be shown to exist. So it's a topological insulator where you have protected Dirac cones only on certain phases. So on the 001 phase, you do not have any protected surface states. You can imagine it as a stack of quantum spin Hall systems. And this has indeed a band gap of around 200 millivolts, which is quite large, but it's, well, based on experiments in our group, it is possibly hard, it's very hard to exfoliate this to the monolayer, possibly because of the ionic bonding in this material between the layers. But it has been shown by STM that it does indeed host edge states, and these edge states have been characterized quite well. Now, so here enters our material, this platinum mercury selenide that I want to talk about, and this has been indeed discovered by the group of Nicola Mazzari in this Fischer-Leathers paper that I show on the bottom, where they've shown that is indeed a Payne-Mealy insulator in the monolayer. And this is because you can just disregard the selenium and platinum atoms that I've just taken out. And the bands around the Fermi level are basically dominated by the platinum, this honeycomb lattice of platinum and mercury that you can see here. And if you just take out spin-orbit coupling, which you can do in DFT, you can see that this indeed has a band structures very similar to graphene. It shows a Dirac cone. But if you switch on spin-orbit coupling, you get a band gap which is quite large, well above 100 milli-electron volts. Now, the material itself has been discovered in 2008, and it is a mineral. So, regarding our wish list of 2D materials, 2D topological materials, well, it's a mineral. It should be stable under ambient conditions, and not just ambient conditions, but temperatures that are, well, relevant to geological processes. Yeah. So. It's been discovered near Rio de Janeiro in Brazil. And the material that we are working with comes from Anna Vymazalova from the Czech Geological Survey. And it is a synthesized material. So it's not the natural crystal, but it's made from, it's made synthetically, it's grown. So this, here I have to say a very big thanks to Anna for providing us with a lot of samples and working with us very closely to try to improve the crystals. And most of the STM measurements that I will show you have been done by Konrad, my student in my group. So here you can see some images of this material. So what we did is we just take the material from Anna and exfoliated it with Scotch tape onto a gold surface, which makes STM investigation easy. And here you can see some crystals of the material on this gold 111 surface. If you take low magnification STM image, you can see steps on the surface that are very similar to what you would expect for Van der Waals layered material. And you can also maybe see that most of the steps have around 30 degrees angles. So this is very indicative that the cleavage plane within the layer is along some crystallographic directions, which turned out to be the zigzag directions. Now, if you zoom in with the STM, almost immediately at measuring in the conduction band of this material, you can see this honeycomb lattice appearing, and it is, well, it's not the honeycomb. It's not quite the honeycomb lattice of graphene, because it has a so-called sublattice symmetry broken structure, whereby one of the sublattices shown by the rectangle here and the other shown by the triangle are not of the same height. And this is quite expected, because if you look at it from the side, one of these sublattices is on the bottom of the layer, and the other sublattice is on the top of the layer. So this results in this sublattice symmetry broken STM image. Now, if you go and look in the bulk and measure STM spectroscopy, which is, as you well know or might know, it is proportional to the local density of states under the tip. You get this blue curve, which shows basically a gap of around 110 millivolts. And if you calculate the density of states of the monolayer, without GW mentioned in parentheses, you get something very similar. You get a very similar density of states as the experimental one. One major difference is, and some of the keen-eyed among you might have noticed, is that the experimental and the theoretical curves are shifted with regards to energy. So the Fermi level in the experiment is here at 0, while the Fermi level in the theory is here at 0. So the crystals in our study are basically very highly n-doped. So there's a lot of electron doping in the system, which possibly comes from defects and impurities in the crystal. So at the moment, the gap is not at the Fermi level, but well below it. But this gap is quite large. It's of course much larger than room temperature, and due to the slightly disordered, well, not slightly, the disordered nature of the crystals, meaning it has quite a few lattice defects, as you can see here in this scanning tunneling microscopy topography image. The band gap tends to vary from site to site. So here you can see a map of the band gap on this area shown on the left image. And you can see in this histogram that, you have most of the band gap values are around 100 milliavolts, but you get much larger values as well. So I think that this 100, 110 millivolts for the band gap is possibly a lower estimate because, just defect states that can show up in your band gap can reduce the size of this in the STM measurements. So if you compare this band gap to other 2D topological materials, like in this website that has been done by the EPFL group, you can see that this is quite large with respect to other 2D topological materials. So it's only surpassed by the monolayer of bismuth, basically. So this looks quite promising from this point of view. Now, of course, this material should host some edge states, and in the case of many other 2D topological systems, like tungsten telluride, like bismuth rhodium iodide, like the transition metal dichalcogenides, usually the top layer of the material behaves quite similarly to the monolayer. So this encourages us to just look at the edges or monolayer step edges on top of the bulk crystal and try to find the edge states. And indeed, if you find one of these monolayer edges, which you can see here, and you do tunneling spectroscopy, getting closer and closer to the edge, you can see that the gap here starts to fill as you approach the edge of the crystal. So this is a very good indication that you have some states appearing in the band gap. Now, if you just go to this energy, to this voltage, and do a mapping of the whole of this whole step edge, you can measure this local density of states as a function of position quite well, and you can see that just at the edge you have a increase in the tunneling conductance, which is again indicative of an increased density of states within the band gap. If you do the similar experiment, but now in the conduction band, you can see that there is basically nothing at this edge, and the tunneling conductivity is just modulated by the atomic lattice, and not much else happens. Now we tried to reproduce this using DFT calculations, and for this we took, maybe I'll skip some details of the DFT. We have been able to identify that in our experiments we most probably have a selenium terminated edge, and calculations for this selenium terminated edge show here your topological edge states for this nanoribbon geometry, which are shown in red here. And now if you do calculated density of states for this edge in the conduction band on the left and in the topological gap on the right, you can see that the image, well, it fits quite nicely to the experiment. The extent of these edge states is basically proportional to, inversely proportional to the size of the band gap. And because the band gap is so large, this edge state basically decays within 5 angstrom into the the bulk, and this is also what we see in the DFT calculation. Now, to get an idea of, so we see that we have some increased density of states at the edges, but this says nothing about the topological or non-topological nature of these edge states. And one of the experiments that you can do in STM is try to look for a lack of backscattering. Of course, it's always hard to prove the absence of something. It's easier to prove the presence of something, but here we try to prove the the absence of backscattering. But nonetheless, STM is well known to show basically interference patterns of trivial electronic states around defect sites. So what happens is basically your electron comes in, gets scattered by a defect. For example, here, this small notch or this small adsorbate here at the edge, it can scatter your electrons. And this results in a standing wave in the local density of states, which STM is very sensitive to. So what you can see, sorry, or what you can do is you can look for what kind of standing wave wavelength we expect based on the dispersion of the topological edge states along the edge. And here I've shown at the energy we've measured, so in the middle of the band gap, you would expect basically a wavelength of these standing waves of the order of 13 angstroms. So what you can do is you can take the density of states measurement along the edge and do a Fourier transform along the edge and look for what kind of periodicities you have there. So of course, one of the periodicities is the 7.3 angstrom of the unit cell periodicity. This, of course, you expect to have in there. You can also see it on the calculated DFT image. But if we do a Fourier transform along this edge, you can see that at the expected wavelengths of the backscattering, you have no signal. So this is an indication that indeed, backscattering is suppressed in these edge channels, as it should be for a topologically protected edge state. This even works if you take a very disordered edge. So this is just a straight edge that I've shown you, but here you can see this very winding edge, which has a lot of adsorbates and defects, and it's not crystallographically perfect. But still, you would expect to see an increased density of states, which we do. And if we again do this Fourier transform of the signal along this edge, you can see that there is a very clear absence of the intervalley or this kind of scattering between the forward moving and backward moving electrons along this line. So this is again a good example of what a topological edge state should look like. Now, we've also done some experiments in trying to exfoliate this material, and well, it's a little bit more difficult to exfoliate than graphene for sure, mostly because the crystal is not as strong in the in-plane directions, so it fragments a lot. But we have been able to show that, for example, you can exfoliate them down to about 5 single layers. And we've also used this Lego technique, or this stamping technique that is so well known in the 2D materials community, to place these crystals, these thin crystals, onto another 2D material, in this case graphite. And you can see the result of this here. So this basically shows that it's possible to combine this material with other 2D materials using well-established methods. So as a few last thoughts, of course, I have to mention challenges and problems. And one of the problems in this case is that we have this very large level of doping of the order of 10 to 14, which it has to be reduced for this material to be used in, for example, a transport measurement. I haven't included here in the slides, but if you look at very thin crystals of these 5 or 10 monolayers, this doping becomes much less. So this could be an indication that indeed some non-stoichiometric impurities or something very similar is at fault here. So basically we have to grow better quality crystals, and also we still have to we have to crack the exfoliation down to a monolayer. We have a special technique whereby we can exfoliate almost any chalcogen terminated material onto gold. And we have been able to produce layers of this material which have a height of 1.3 nanometers. So this is getting very close to the monolayer. However, the crystal structure of these exfoliated material is not very good. So we're still working on the monolayer part. Now, from challenges to opportunities, the story of this material is by far not over. So it has been shown in the first paper by Nicola Marzari's group that due to the fact that the 2 sublattices are located on either side of the monolayer, this material is susceptible to changes in the band structure when you apply an electric field that is perpendicular to the layer. And they have shown theoretically that you can switch the material into a trivial state if the out-of-plane electric field is large enough. So basically, this could be a switchable topological insulator in the monolayer. Now, for the bulk, things get more complicated and more exciting. So it has been shown by the 2 groups, basically. One of them I forgot to include here, sorry, that the material, in addition to being a weak topological insulator in the bulk, so basically a stack of 2D topological insulators, it is also it should be a crystalline insulator, meaning that it has a mirror Chern number that is non-zero, and this leads to certain Dirac cones within the bulk band structure. Now, these Dirac cones are located and are overlapped with bulk states. This makes it a little bit difficult to investigate this in STM. Not impossible, but difficult. And it has been shown using, so these topological, so these mirror protected Dirac cones have been shown to exist using ARPES measurements. Now, as a last thought, it has been also shown theoretically that if you dope the material to these Van Hoff singularities in the band structure, either this one in the bottom, so in the valence band, or this one in the conduction band, it is possible that this material will be a D or F wave superconductor. So a lot of exciting physics packed into a very small package. So with this, I think I will finish. So most of the work, experimental work, has been done by Konrad in my group, and I am very grateful to the CIRI help within our group. So for Peter Vancho and Gergő and János from the Eötvös-Loránd University, and of course to Anna for providing us with these samples. And I would like to thank you for your attention.
Okay, thank you, Peter, for this nice presentation. So I think now the floor is open for questions. So I would ask participants, if you have questions, then you either could write it into the chat window, or
will you read the questions, or should I?
Yes, I can read the questions.
I have a question, Laszlo. So
yeah, go shoot. Alberto.
Hi, thanks, Peter, for this talk. I have a quick question. So you said just some slides ago that applying a perpendicular electric field, you can change the topological nature of the ground state, right?
Yeah.
Yeah, right. So is it possible to do the same with a strain?
Well, it's possible. I don't know about any calculations regarding this. Yeah, I would expect that the strain, well, if you're talking about in-plane strain, nothing fancy, it's possible that it could happen, but I would expect the strain to be quite large, because I would say, so for some materials where the band inversion is not due to spin-orbit coupling, for example, zirconium pentatelluride is basically a pi band. It's due to, in that case, the topological nature of the ground state is due to pi band overlap. And by playing with the strain, you can play with the overlap of the pi bands. And for very small strains, it can indeed switch between different topological states. But in this case, it's just the K-milli insulator. So I'm not a theory. I don't know. So I'm not very well versed in theory, but
you mean
I would expect this to be quite large, the strain, what you would apply. Because in the low energy Hamiltonian, where does this go into? I mean, it doesn't do much, right? So just a guess.
No, I thought that, Alberto, if you put a strain on it, could it happen that the two sublattices, the distance between the sublattices shrink? So if you had an electric field and you were in the insulating region, and you apply a strain, and then the electric field will be not that much different in the two sublattices. And you could go back to the quantum spin-out state.
I see.
Yeah, I mean,
okay, thanks.
I thought, I also have one question basically, which is, can you envisage somehow in the future that you can engineer the geometry of the edge of these samples? And if you can, so can you somehow make regions where you could somehow have strongish Coulomb repulsion in part of the sample, in the edge, like making a small quantum dot?
Yeah, I mean, it's not out of the question, but certainly not easy to. So you want to do some, you want to apply some local Coulomb potential to localize electrons. That's what you're looking for.
Yes, and I was wondering whether could that lead to a spontaneous breaking of time reversal symmetry, and whether you could see the time reversal breaking scattering due to those type of effects. So if you don't have time reversal breaking impurities, but you could somehow, if you have some feature which could.
Yeah, I see what. So you're thinking about dipping the gap below the Fermi level, which would induce some mixing of the states. Or?
Well, I would assume. I mean, this would probably work only in a thin sample. So
yeah.
In the topological region, and you somehow could just localize the edge states.
Yeah, it's an interesting experiment. I mean, you can do a lot of things. You can also do localize electrons underneath the STM tip in special cases. So yeah, that's something for the future.
Okay, thank you. So are there other questions from the audience? Okay, there are no other questions, and I think we can thank again Peter for the nice talk. And
all right, thank you very much.
And then we can move on to the next speaker, which is Olivio Giatti.
Yeah, hello.
Can you share your screen?
So I hope you can see it.
Okay, so you have 20 minutes.
Yep. Okay.
Now.
Okay, thank you very much. Today I'm going to talk to you about our measurements of electrical transport properties in vanadium-doped bismuth telluride selenide. the transport measurements were performed in Berlin at the Humboldt University by Christian Ria, Birkan Dützel, and Karl Graser. We also have ARPES measurement performed at the Helmholtz-Zentrum in Bessie 2 by Evangelios Golias and Jaime Sanchez-Barriga. And the material, of course, comes from the Novosibirsk State University, thanks to Oleg Tereshenko. And the results have been published recently in Physica Status Solidi. So, why are we interested in bismuth 2 tellurium 2.4 and selenium 0.6? First of all, the whole mini colloquium is mostly about topological materials, in particular topological insulators. That means we have insulating bulk and conducting surface, and ideally we want these surface states to be topological and form a nice Dirac cone, and with states where the spin of the electrons is locked to the momentum, which reduces the backscattering unless we break the time reversal symmetry. We have seen in our own work on bismuth selenide that in these typical materials like bismuth selenide or bismuth telluride, unintentional doping of the bulk excuse me, can provide bulk conduction states which masks surface conduction. So it becomes difficult in transport measurements to detect and identify topological surface states. One of the advantages of ternary compounds like bismuth telluride selenide is that this unintentional doping can be reduced and therefore can decrease the bulk conduction. For example, in bismuth selenide, we have selenium vacancies, which are reduced if we use bismuth telluride selenide. In bismuth telluride, we have anti-site defects, which provide unintentional doping. And this is also reduced in this ternary compound. So we have an option of reducing the bulk conduction and bringing the chemical potential into the bulk bandgap where we expect to find the topological surface states by using these ternary compounds. In addition, if we use metal atom doping like vanadium, we can shift the Dirac point relative to the Fermi level and the bulk bands. And if these atoms are magnetic, we can also break the time reversal symmetry and induce a gap in the otherwise linear dispersion of the Dirac cone. So previous work on bismuth 2 telluride 2.4 and selenium 0.6 looked at the structure and the effects of the selenium distribution. On the left-hand side, you see the bismuth telluride structure, which is made of quintuple layers where we have one atomic layer of telluride and then an atomic layer of bismuth until they build a quintuple layer. The next quintuple layer is connected to the first one through a van der Waals scarf, which means we can exfoliate this material. But if you want a unit cell for the crystal, you need 3 of these quintuple layers. Now, when we look at the ternary compound, where we substitute one tellurium atom with one selenium atom, usually the central atomic layer in the quintuple layer is the selenium layer, and the other 2 layers remain tellurium layers. So what happens if we change the stoichiometry to some non-integer number? The work published in Physical Review B looked at 2 extreme cases of selenium distribution. In one case, all the selenium stays in the central layer in the quintuple layers with the distribution of 40% tellurium and 60% selenium. The other extreme cases is where selenium is distributed through in all tellurium layers with another distribution. And the work looked at ARPES measurements and density functional theory calculations to see the effect of these distributions. And here in gray and black, we see the ARPES measurement, and we can see very nicely the topological surface states with nearly linear dispersion and the Dirac point down here. And the lines are the results of density functional theory calculations. And we can see that for the blue and the green line, are the two types of distributions of selenium, and it shows that the topological surface states are relatively insensitive on how the selenium is distributed in the crystal. However, if you look at the valence band, you can see there's a big difference between the two types of distributions, which means depending on how selenium is distributed in the crystal, we can expect slightly different band structures and slightly different electronic properties. So in our work, we received some crystals from the Novosibirsk State University grown by Bridgeband method. From these crystals, the Helmholtz-Zentrum Berlin did some ARPES and photoemission measurements, usually in this case at a photon energy of 66 electron volts and a temperature 300 Kelvin. From the same material, we made some samples by cleaving bulk samples, which were about 2 by 5 millimeters big, and with a thickness from 170 to 650 micrometers. So actually bulk samples, not thin flakes. These were then glued on a silicon with silicon oxide substrate and were contacted with aluminum wire and silver paint. With these samples, we could then do transport measurements at the Humboldt University by doing resistivity with the Van der Pau method and Hall coefficient measurements in a flow cryostat with relatively low perpendicular fields. And in a second system, we performed magnetoresistance measurements down to 0.3 Kelvin with fields up to 2 Tesla. So if you look now at the vanadium bismuth telluride selenide samples, we have some ARPES measurements for 2 samples of different vanadium concentration. One is 1.5% and the other one is 3.0%. The sample with lower concentration shows very nice topological surface states with a Dirac point at 0.33 electron volt binding energy. We see the bulk valence band, and we see that the chemical potential is seems to be in the bulk band gap. Increasing the vanadium concentration seems to shift the chemical potential to higher energies. That means the binding energy of the Dirac point becomes larger, and we start seeing the effect of bulk conduction bands, which means in both samples, the chemical potential seems to be fairly close to the bulk conduction bands, which should yield some effects in the transport measurements. So if you look at the temperature-dependent resistivity, we've measured from 300 Kelvin down to 0.3 Kelvin, and we see at higher temperatures that both samples seem to be have a temperature dependence typical of a semiconductor. However, below 20 or 10 Kelvin, the resistivity seems to saturate to constant values, which is something we expect if surface states like topological surface states are short-circuiting the bulk conduction. So we expect the higher temperature to be dominated by bulk conduction and the lower temperature to be dominated by surface states. If you look at the results of the Hall measurements and we calculate a one-band charge carrier density from the Hall coefficient, we see that this carrier density decreases with temperature until about 20 or 40 kelvins, like we expect in a semiconductor, and then it saturates at a constant value, which is what we would expect from a surface states like topological surface states. What we didn't expect is the minimum in the charge carrier density of the sample with lower vanadium concentration. We're not sure yet why this happens, but we can see that it still saturates at lower temperatures. Having the resistivity and the charge carrier density, we can also calculate the one-band Hall mobility, and we can see that at high temperatures, the temperature dependence looks a lot like a semiconductor, but it reaches a constant value at lower temperature, which is also something we expect from topological surface states. However, again, we have a surprise here that the mobility of the sample with lower vanadium concentration is definitely lower than the other sample. We can do some further analysis of these results. In particular, we can do an Arrhenius plot for the charge carrier density. We already see that it's an n-type conduction, so these are electrons. And at higher temperatures, the charge carrier density is thermally activated, and at lower temperature, which are not depicted here, it saturates. From the Arrhenius plot, we determined from linear fits some activation energy, and we can see that at lower vanadium concentration, the activation energy is larger than by higher vanadium concentration, which is consistent with the ARPES picture, which shows that the chemical potential moves closer to the conduction band. In the mobility, the picture is a bit more complicated, and it's a hint that maybe a one-band analysis is not entirely suitable for this system. We see at high temperature that the temperature dependent fits very nicely the electron phonon scattering in semiconductors. At lower temperatures, it's more complicated. It looks like we have a temperature dependence consistent with an activation across a barrier, in addition to a constant offset. This could make sense if you assume that the surface states are shunting the bulk conduction, and the bulk conduction has a barrier-like activation. We also performed some fits to get barrier heights, but how to interpret these numbers is not entirely clear yet. What we can say that above the by temperature, we have probably bulk conduction that will looks like electron phonon scattering in semiconductors. At lower temperatures, it's a bit more complicated. So the magnetotransport at low temperatures shows dips in the magnetoresistance around zero field. And we see that these dips are consistent with weak anti-localization. So the topological surface states are still spin momentum locked, like we expect in without in a normal topological insulator. And we can see that the dip disappears if we increase the temperature. So at 10 Kelvin, the dip is not sharp anymore, but it's around here. The same goes with for the sample with higher vanadium concentration, but the temperature where the dip disappears is lower than in the other sample. What we also observe is something that looks like a hysteresis here, which disappears at higher temperatures. And it depends on the sweep rate of the magnetic field. And it's still not clear what is the origin of this hysteresis. Having now dips in the magnetoresistance, we can apply the Hikami-Larkin-Nagaoka fit to extract some data like the phase coherence length. And we use a typical fit function for two-dimensional systems with a strong spin orbit coupling. And the fit parameters are the parameter alpha, which depends on the number of conducting channels, and this parameter BFE, which depends on the phase coherence length. Now, we have already seen in our work on bismuth selenide that alpha can be large if we have more than one conducting channel, which is a hint that the conduction in a system like this can be more complicated. On the other hand, the phase coherence length is more robust in the fits and doesn't depend on the number of the conducting channels. So if we plot this as a function of temperature for the different curves, we see that the phase coherence length decreases with temperature as we expect. The values for the alpha parameters are still large, which is a hint that we don't have one single topological surface states conducting, but we have a bit more complicated system. And so to summarize, our measurement results indicate through ARPES and the low temperature saturation of the charge carrier density and the mobility and the weak anti-localization that we have topological surface states. But at high temperatures, we can say also that we have a bulk conduction, which comes from thermally activated carriers into the bulk conduction band with electron phonon scattering. What is left to this, the challenge for our outlook is that we probably need to apply a multi-band channel analysis to get a better idea what the conduction is at lower temperatures, which needs magnetotransport measurements at higher fields. And we have left to work out what is the origin of these sweep rate dependent hysteresis. So if you're interested in the work, please have a look at the paper, and I thank you for your attention.
Thank you, Olivier, for the nice talk. So if there are any questions from the audience, then...
Yes, I do have a question. May I?
Yes, yes, sure.
Oops.
Yeah, it's about what you said about this hysteresis in magnetoresistance.
Yep.
Do you have any clue? So is there any magnetism effect involved? Is something, do you expect something like this?
We don't expect an hysteresis like we see in with ferromagnetic materials. What we observed here, for example, is if you sweep the field and then we stop sweeping the field and sit there for a while, the resistance changes with time until it stabilizes. And it doesn't seem to depend on the how long it takes, doesn't seem to depend on the sweep rate. And but it seems to depend in which direction we sweep the field. So we don't think it's a ferromagnetic. We don't think it's a simple heating effect due to eddy currents, because it doesn't fit the the time dependence of the resistance. We have some ideas that it might involve eddy currents with the surface states, but the idea is not quite fleshed out to explain properly this effect. But we can say it's not ferromagnetic or simple heating due to eddy currents.
Okay, thanks.
Okay, thank you. Are there any more questions? So if there are some questions, then write again to the chat.
Yep.
But if there are no questions left, then I think we can thank Olivier again for the nice talk, and we can move on to the next speaker.
Thanks
So,
to you.
Thank you. So next speaker is Helena. Please, Helena, share your screen and tell us about the interacting Su-Schrieffer-Heeger model.
Yes, I first would like to thank the organizers for giving me the opportunity to present our research on interacting Su-Schrieffer-Heeger chains. And I would like to start with reminding everyone what Su-Schrieffer-Heeger chains are. So in a Su-Schrieffer-Heeger chain, a particle hops on a linear chain, which consists of two sublattices, and it has two different topological phases. The first one is the trivial phase, where the intra-pair distance b is small, and therefore there's a large hopping probability within the pair. And the second one is the topological phase, in which the intra-pair distance is larger. So the intra-pair hopping is not very probable, but there's a higher hopping probability between neighboring pairs. In this topological phase, we have edge sites on the left and on the right side of the chain, and these edge sites host topological edge states. Originally, this model was built for modeling linear molecules, but current experiments are usually done having a single atom in a linear atomic trap. My title promises interacting Su-Schrieffer-Heeger chains. So in order to have interaction, we need at least two particles. And these two particles are located somewhere on the lattice at lattice sites X and Y. And I will now explain you how this problem of two particles in one dimension is mathematically equivalent to having a single particle in two dimensions. So the coordinate of the first particle here will be the X coordinate in our 2D system, and the coordinate of the second particle will be our Y coordinate here. Of course, if you have identical and indistinguishable particles, you cannot say which one of them is the first and which one is the second particle. So you could also switch them, and then you have a mirror symmetry in this two-dimensional system along the axis of X equals Y. now we want to have an interaction between these particles, and this interaction could, for example, be a repulsion. And we assume that the particles repel each other if they're on the same lattice site or on neighboring lattice sites, but if they are further away, that there's no interaction between them. And this corresponds to different on-site potentials along and next to the diagonal in this two-dimensional system. The SSH chains have a hopping of the particles, and if we assume that only one particle hops at a time, that corresponds to hopping in a so-called von Neumann neighborhood, which I have marked here. And if we assume that both particles can also hop at the same time, that corresponds to hopping in a Moore neighborhood. Now let's take a minute to think about which states we expect for this system. So I said that there's a repulsion along this diagonal where I marked the lattice sites in yellow. So we expect the states to be localized away from this diagonal due to the repulsion. And indeed, that's the first states that we find. I call these normal states because they are, as we have expected, far away from the diagonal. But once these normal states have occupied all possible low energy states, at higher energies, there are also so-called Duplon states, which are localized along the diagonal. And why are they called Duplon states? So if we go back to the one-dimensional system, this diagonal here corresponds to both particles in the 1D system being on the same lattice site. So these are the possible states in the trivial phase, and of course in the topological phase. We also find these expected normal states away from the diagonal. But we, of course, also find some edge states, as we already had in the one-dimensional SSH chain, and we have corner states. And then again, we find these Duplon states. So that's very already interesting. We have these states in the trivial and the topological phase, but what we really want to do is have transitions between these two phases and investigate how the states evolve during these transitions. So let's first go back to the 1D system and how a transition could take place here. So you can see here a 1D SSH chain in the trivial phase, marked by these black dots. And then the arrows already show you what you have to do in order to get from the trivial to the topological phase. So now you move them, and they move. And now we're in the topological phase. And if we do not want to introduce disorder, that's the only possible transition to get from the trivial to the topological phase in this 1D system. In 2 dimensions, there are several different ways to get from the trivial to the topological phase. And here again, I show the system in the trivial phase, and these arrows will show you how they move to get to the topological. So now they're in the topological phase, and then in order to get back, they just follow the same path in the opposite direction. So because it's the same path to get from trivial to topological and back, we call this transition time reversal symmetric. In this transition, all the sites just move in one single direction along this line in 1 dimension. But of course, we have this whole 2D plane available. So we could also have transitions that use the whole plane. For example, this counter-rotating transition that I show on the right side of the slide. Here again, we start in the trivial phase, and then the lattice sites will move along these circles to get to the topological phase, which they reach now. And then what's interesting about this transition is that the sites do not take the same path back. So they continue on the circle, and the whole transition is not time reversal symmetric. So how would we go about having this in a real experiment and not just in a theory? So I said before that the 1D SSH chain is implemented by having an atom or a particle in an atomic trap. And of course, you can also have 2-dimensional atomic traps, which are then called optical lattices. And if we have one particle here, we can have all the parameters that I've shown before for the theory. So we can adjust the hopping probabilities by having different lattice spacing. and the on-site potentials along the diagonal would just correspond to the potential depth of these ion traps here. But as you can imagine, it might be tricky to adjust all these different potential wells in just the right way to have a transition like this rotating one that I showed you before. So another experimental realization could be in so-called optical waveguides. And in these optical waveguides, the particles that move are light. So we could start at one side of this optical fiber, and couple light into it, and then the transition takes place while the particle or the light moves through this fiber. So the transition time corresponds to the distance that the light travels through these waveguides. These waveguides can be written into the material at any position, so that can adjust the hopping between them. And the onset potential corresponds to the refractive indices of these waveguides. What's really cool about this is that these waveguides can not only be used to model our theoretical calculations, but that they also constitute a useful application. So if we, for example, imagine that we could find an effective transition from the trivial Duplon state to one of the topological edge states, then that would mean that we steer the light between these states, and so they switch from one fiber to another, which could be very useful. So back to the different transitions that I've shown you. Here on the left, again, there's a sketch of this linear transition. And on the right, there's a plot of the orbital energies of all the different states that I've shown you before for the trivial and topological phase. And you can see that in the trivial phase, all these states are sorted into a few bands. And then in the topological phase, there are also bands, but there are more of them, and that's due to having these edge and corner states. During this transition, right in the middle between trivial and topological, we have a configuration where all the lattice sites are equidistant, and that's in the middle of this plot on the right-hand side. And you can see here that all the bands are merged into one, and you can imagine that it would be very hard to follow one specific state from the trivial through this part in the middle where they're all very closely spaced over to a specific topological state. So that might be easier in the other transition, the counter-rotating one. As you can see here, again, we start with the trivial phase and we end at the topological phase. But in between, these bands are still well separated from each other. So sometimes they cross or merge, but overall, there's much better spacing between all these different energies. And that's, that can be explained if we look at this movement again. So if we let this run a little bit and then just stop it at some random time, you can see that in the X direction now, it is in the topological phase, and in the Y direction, it's in the trivial phase. And that's true for all times. So it's always in either the trivial or topological phase in at least the X or Y direction. And that's why we have this nice spacing here in between, and not this very close spacing and just a single band that we had before in the other transition. So the problem with these plots that I show on the right side is that all these orbital energies were calculated separately for each of the intermediate steps. So I made one calculation here for the trivial phase, and then one for topological, and for everything in between. So there's no real notion of a transition time or driving frequency. This plot corresponds to having an infinitely slow transition from trivial to topological. So that means that it's perfectly adiabatic. But of course, infinitely slow also means that we cannot do that in experiments. Infinitely slow times would correspond to an infinitely long fiber, and that's not feasible. So we want to also study the influence of the speed of this transition. And in order to do that, we use Floquet theory. And Floquet theory is basically analogous to Bloch theory, but instead of being periodic in space, as the Bloch theory, it's about a periodicity in time. So we imagine that this transition from trivial to topological and back repeats several times. And if we look at this formula, the Floquet Hamiltonian is calculated from the time-dependent Hamiltonian, which is multiplied by an exponential term which goes with the transition period times the time. And then it's integrated over this. And then there's another term for having the different Floquet blocks, which goes with n times omega. So you can think of this as an kind of an average Hamiltonian, which does take the time ordering into account via this exponential term here. And now we calculate the Floquet energies of this Hamiltonian. And I plot these here. So this is for the zeros Floquet block, where the explicit time dependence all cancels out. So if we plot the Floquet energy over a wide frequency range from 0 frequency to 3 atomic units, then we see that all these energies are constant. And so this is the zeros Floquet block. If we take the first, then it has a slope of omega, the second of 2 omega, and the third of 3 omega. But that was all to be expected. So that's usual for the Floquet theory to have these different slopes. What's the interesting feature is not the slopes, but the crossings between the different Floquet blocks. And to see that, I will zoom in a little bit in roughly this region here. And again, these horizontal lines are the zeros Floquet block, and these diagonal ones are the first. And if we follow, for example, this orange line here from the zeros Floquet block, you see that it bends up here, and that's because it has an avoided crossing with this highest energy state from the first Floquet block. And then it continues here, has some real crossings with some other states, and then here it bends again, and that's due to a wider band gap avoided crossing with this other state here. So these crossings and avoided crossings are the interesting parameter spaces. So right now we're working on performing real-time simulations of these transitions at exactly these frequencies. And in order to have experiments at these frequencies, you would need to adjust the refractive indices and the spacing of the waveguides so that the transition frequencies correspond to realistic length of fibers. So you have fibers of a meters length and not kilometers length. To summarize my talk, I have shown you how two particles on a one-dimensional Su-Schrieffer-Heeger chain are identical or mathematically equivalent to having one particle in 2 dimensions. I've shown you the different states of the trivial and topological phases, as well as transitions between these topological phases. And I've shown how we use Floquet theory to identify interesting parameters for the real-time calculations, which we are working on right now. And the ultimate goal of this research would be telling light how to move through an array of optical fibers. Thank you for your attention.
Thank you, Hannah, for the nice talk. So if there are any questions regarding the presentation, please you should type in the chat window.
I have a question, Lasse. Perhaps it's a little bit not totally related to the results you presented. It's more about the goal you present at the end. So when you consider the case of fiber optics, like the Summit and these and co-workers, how do you introduce interactions in these optical settings? Because it's classical light, so you consider nonlinearities or something like this?
Yes, so for what you can adjust in these optical waveguides, you have the 2 parameters, and one would be the spacing. So if you write these waveguides into the material, you can write them at any position you want. So you could have them closer together, so there's a higher hopping probability of going from one fiber to the other. And the interaction that I talked about of a different potential on the diagonal, that would be waveguides which have a different refractive index than the other ones around it.
Okay, but not local nonlinearity like the Pockels effect or something like this, or the nonlinear optical Kerr effect. nothing that mimics the two particle interactors, something like this, right?
No, no, because we have
single
this.
particle.
Yes.
Okay, thanks.
Okay, are there any more questions? So if there are no more questions, I think we can move on to the next speaker of today's session. Who is, sorry. Yep. So Gerard Valentin-Roes should come.
Yes. Can you see me?
Yes.
Okay. So let's see if I can share screen. All right. Should I start then?
Yes, and you have 20 minutes.
Okay. Well, thank you. Thank you very much for the introduction. So I would like actually to start by thanking the organizers for giving me the opportunity to speak here today to present our results. So the title of my talk is Synthetic Flux Attachment, or How to Make a Chern-Simons gauge field come to life. So this theoretical work, it's a joint effort between Patrick Huber, Nicholas Westerberg, and myself at Harvard University. And it's actually a story about gauge fields. And as such, I think that the proper thing to do, is to start by explaining what I mean by a gauge field. And what I mean is just the generalization of the concept of a vector potential that we all know from conventional electromagnetism. So a good way to illustrate this concept, I think, is to think of a charged particle in a magnetic field, right? So if you go to your favorite textbook, you will verify that what couples at the level of the Hamiltonian is not the magnetic field itself, but the underlying vector potential. And it does so in a rather nice way, right? Through minimal coupling, or if we are in the lattice, through chiral substitution. In any case, we have a well-defined mathematical scheme to couple gauge fields to matter entities. So with this picture in mind and with this example in mind, I want you to think of the following question. So if the magnetic field here is some external parameter, does this Hamiltonian formalism constitute a gauge theory? Well, you can certainly write down a Schrodinger equation for this system, and you can verify its gauge invariant and so on. But I would argue this is not a gauge theory because the gauge field here is a background entity. It doesn't have dynamics. So what is a gauge theory? Well, we can say it's a description that involves gauge fields as well, but where the gauge field here are the dynamical entities, meaning that they have their own equation of motion. But not only this, they must also couple and backact on matter, and we want also local constraints in the form of Gauss's laws to be satisfied. So with all this, we end up with a sort of checklist to see whether or not we have a gauge theory or a mere theory coupled to background gauge fields. And this distinction, although subtle, is important because there's interesting phenomena that have to do with fractionalization, with the generation of dynamical mass terms and confinement physics that have to do with the fact that the effective theory is a gauge theory. And with this distinction, I think that we are ready to sort of face the conundrum here, which is how do you go from one to the other? How do you start from our initial description, right? That was not a gauge theory and go all the way to a gauge theory. Well, one thing that you can do, a lazy thing that you can do is to supplement the non-gauge theoretic description with a constraint. And this constraint can be, say, that the vector potential or the gauge field is a function of matter density. And if you do that, what you're doing instantly is checking item number 2, dynamical gauge fields of the checklist, because you see if the matter satisfies an equation of motion, namely Schrodinger equation. If you have a function of it, it must do so in a similar way. And this is interesting, and we should care about this because nowadays people in ultra-cold atoms are able to experimentally engineer this kind of constraints, this kind of supplementations. I know of at least 3 recent works where people have been able to engineer chiral spaces that depend on matter density. And if experimentalists can do that, I guess we as humble theorists, we should ask ourselves, what can we do with this, whether this is interesting, and whether that relates to the real world, And in fact, I'm here to tell you that, well, we think this in fact relates to the real world and to very interesting physics, in fact, to the physics of fractional quantum Hall effect, and maybe more generally to topologically ordered phases. So let me tell you what I mean by flux attachment first. So for me, flux attachment here is a physical mechanism by which charged particles, like electrons, capture magnetic flux quanta and become composite entities. So you have a depiction here on the bottom right. So, and as a consequence of this dressing, they effectively become anionic particles, like with fractional quantum numbers and statistics and so on. And this can be seen if you know a little bit about field theory. This can be seen very easily from the Chern-Simons term. So if you write down the Lagrangian density for an abelian Chern-Simons term here, A is the gauge field, F is the usual the usual F tensor. So you can write the Euler-Lagrange equation of motion in the presence of a matter source here, right? Where J here contains the matter of the theory, and you can write this if you want in components and verify that the magnetic field is essentially proportional to charge density, and this is a quite bizarre relationship if you think about this. So if you have an electron that satisfies this relationship, well, this is telling you that not only you have charge, but you also have magnetic flux following it. Sort of if the electron here had effectively eaten a magnet, which is I think it's very cool. But in any case, this a bit more formally what people mean by flux attachment, and you can actually simplify this a little bit more by taking the curl to the right-hand side of the equation. Of course, you have to fix a gauge. If I fix Coulomb gauge, I obtain this relationship, right? But you see, this is nothing but a particular example of what I was mentioning before of this supplementation or this constraint, right? Of a density-dependent gauge field, right? So a relationship between the gauge field and charge density or matter density in this case. So you see, we can think of Chern-Simons term as a way to essentially supplement this constraint in a natural way. And we can use this essentially to try to engineer a Chern-Simons term. So if you, just to put it more plainly, my goal here is, starting from a microscopic interacting quantum many-body system to see if I'm able to derive the emergence of a Chern-Simons gauge theory so that it performs flux attachment in a tunable way, right? And of course, this is not free of setbacks and challenges. So for instance, one of the most prominent ones is that flux attachment is an emergent property, right? So we don't really know what's going on at the microscopic level. All we know is that, we have a many-body system that will rearrange itself in such a way so that the physics of flux attachment pop up at a macroscopic scale, at a phenomenological level. So we know what is our end goal, but we don't know really what is the microscopic initial, starting point, right? And in addition to that, if we want to engineer something, if we want to come up with an experimental scheme or proposal, we have to choose a platform. And if we choose ultra-cold atoms, this is a platform that is very dilute, and atoms are charge neutral. So we have two extra challenges. The first is that it's dilute, because if we want to explore the physics of strongly correlated phases, well, if you use a dilute system, this is sort of paradoxical, but the fact that it's charge neutral is even worse than that, because the usual minimal coupling scheme doesn't apply anymore because there's no net charge to begin with. But well, there's all sorts of ways to surpass these sort of challenges or setbacks. One of them is to use synthetic gauge fields. Now, I won't comment further on this, but I refer you to the literature and even to Wikipedia to read more about this. Instead, what I will do is just to flash the proposal that we have in mind in our scheme and try to walk you through this. So let me see. So what you're seeing here is a quasi two-dimensional Bose-Einstein condensate made out of ultra-cold atoms. And these atoms interact pairwise and have some internal structure, right? Now, we will demand that this Bose-Einstein condensate is illuminated by a laser beam that will coherently couple two of the internal states of these atoms. In addition to that, it will carry orbital angular momentum. And what this will do is it will nucleate a vortex in the cloud. And we will argue later on that this vortex has rather nice properties. Sorry. So, you know, you have the illustration, like me walk you through the microscopic model. So what we have here is a, you know, a microscopic many-body Hamiltonian for this BC plus laser system. And it's very simple. It consists on a kinetic term, on an external potential that you can think of as a trapping potential that doesn't allow atoms essentially to fly away to infinity. And of course, we need like matter interaction because we want to couple the laser beam to the internal level of the atoms. Now you can think of this like matter interaction U as essentially a 2x2 matrix for each particle times a coupling constant given by omega, that is called the Rabi frequency, that essentially provides the relevant energy scale here. And well, this is like matter interaction. Of course, we need also interparticle interactions here in blue. We will consider that atoms interact pairwise in a super short range fashion, right? In fact, via delta function potential, and with some coupling constant G that will depend on the internal state of the colliding particles. And well, this is how an atom looks like for a theories, I guess, in this case. So what you see here is an incoming photon from the laser beam with frequency omega, and two internal states of the atom, 1 and 2, and level spacing omega A. And there's a slight detuning, a slight difference between these two frequencies given by delta, and this will actually provide the tuning knot for the experimentalists, we believe. So what's remaining here for me is to tell you about the relevant states in the system. So you see here I have plotted the bare states, the physical states of the system, 1 and 2, but these are not actually the eigenstates of the single particle Hamiltonian. In fact, the eigenstates, also called the dressed states of the system, are these plus and minus. So I guess the most useful thing I can say about this plot is that you can think about this in a sort of band theoretical way, as if you can prepare essentially your Bose-Einstein condensate in plus or minus, and there's some energy gap given by omega here, right? So, okay, now we have our microscopic model. We want to get an effective description. So what we can do is essentially approximations. So let's see. The first thing we can think of, probably, and this is a standard practice in the field, is to consider that the system is extremely dilute. So what this allows us to do is to essentially factorize the many-body wave function in terms of single particle wave functions in order to obtain a sort of mean field single particle picture of the Hamiltonian. Essentially, we drop the sum and we obtain a mean field Hamiltonian. Now, as I was saying, this is standard practice, so I won't comment further on this. Instead, I want you to focus on this second approximation, which is the fact that we will require to be in this regime where like matter interaction is much, much stronger than interparticle interaction. Again, this can be thought a bit as a consequence of the fact that the system is very, very dilute and therefore wiggle interacting, but also because there's some range of tunability in both these interactions, we believe, at an experimental level. So again, interparticle interaction will be very small, and we can use it to essentially perturb the like matter coupling matrix. This will allow us to, in turn, essentially expand perturbatively the eigenstates of the system, and this perturbation will depend on the kind of interaction, of interparticle interactions that we've introduced. And since the interactions we consider are density-density, this perturbation will depend on matter density ultimately. So what's remaining is just to tell you about the last approximation here, which is the so-called adiabatic approximation. This one is very straightforward. So if you prepare the system in the minus state, it will remain in minus state for the whole process, for the whole experiment, or in plus, right? And in some way, we're saying that we don't allow interband transitions at any point. And this is important because then we can effectively project the system in the subspace in where the physics takes place. So we take the mean field Hamiltonian and project it into the plus or minus subspace within the Hilbert space. And this effective description, this projection, will be valid as long as we don't get out of this subspace. So that's essentially why you have this plus and minus sub indices here in depending on whether you prepare the system in plus or minus. So now we have an effective Hamiltonian. What we can do is to get an effective Lagrangian, and this constitutes essentially our effective model for the Bose-Einstein condensate here coupled to a laser beam. Now, this very simple model, but we managed to recover essentially a Chern-Simons gauge theory. So the first term is a Chern-Simons, an abelian Chern-Simons field. We have minimal coupling to two gauge fields, capital A and small a, which small a is the Chern-Simons gauge field. We also have, say, a 5-4 term and a mass term that is not too relevant here. Instead, what I want you to focus your attention on is on the fact that the gauge fields here are very connection terms. And they come about because of this projection that we've done and because of the perturbative expansion, right? So we have two terms that can be traced back. So its origin can be traced back to the original terms in the microscopic Hamiltonian. In fact, the capital A gauge field is a background gauge field that comes because of the single particle contribution of the initial Hamiltonian, while the Chern-Simons gauge field comes about because of the interaction term, the interparticle interaction term that we've added as a perturbation. So to some extent, we managed to get out of short-range interparticle interactions an effective Chern-Simons term, at the macroscopic level. Now, what's remaining for me to say is that, well, we could analyze this model, but this was already done in the 80s and the early 90s because this so-called the Zhang-Hanson-Kibelson model, and it was a model that was used to describe the macroscopic or composite boson description of a fractional quantum Hall fluid. And instead, I refer you to the super nice review from Zhang, where essentially many quantities are computed and several predictions and phenomenology is discussed. And I would like to comment further on this, but I'm running out of time. So the last thing I would say is that, as I was promising, these vortices that will form in the system that will be induced will in fact be anionic because there will be flux attached to it that we believe can be tuned by means of these laser matter coupling parameters, right? So they will be essentially fractionally charged and will have anionic statistics, and in principle you can do the braiding experiment and so on. So with this, I would like to come to a conclusion by essentially quoting a caption from this super nice book from Girvan and Yang, published last year, saying, to date, experimentalists have not succeeded in performing this operation, referring to flux attachment. We believe that maybe with our work, we're a step closer to help experimentalists succeed in performing and maybe tuning at will flux attachment. Thank you.
Thank you for the nice talk. Are there any questions? So if there are some questions from the audience, then please type it in the chat, or if there are some.
I do have a question, if you mind.
Okay.
Yeah, thank you for the talk. So maybe the question I'm gonna ask is a little bit off topic, but
sure.
Apart from this flux attachment, is there only any way to measure this gauge dynamics in collatoms? For instance, what would be the equivalent to a transport experiment in these collatom settings?
So you mean like like measure Hall conductivity or something like this?
Yeah, something like this.
So I mean there's I mean, transport experiments in cold atoms is something that people struggle with. But
there are experiments in cold atoms, right?
Sure. And there's actually some proposals to detect sort of a Hall resistance by essentially making an analog of a Hall bar, and instead of thinking of electrical current and so on, thinking more in a fluid dynamics kind of picture, where instead of where you create a tilting potential and you expect a Hall response in the transverse direction. But other than this, I cannot think of many things that people can measure. Instead, what I would do, maybe this doesn't apply generally to gauge stuff, but for this, in principle, if one can make sure that to induce one of these vortices, one could imagine creating another one and doing the braiding experiment, or but this would be more static. So the short answer is I'm not too sure about transport experiments. It's a challenge.
Okay, or transport or time of flight. We heard about this yesterday, I guess. So it's because, as you said, flux attachment is very cool, but okay, how do we see it?
Yeah, I would say that the way to see it is not right. So you don't. I don't know if you can observe directly flux attachment, but you can observe the generation of an anionic vortex. And if you observe that, I mean, I believe that is, you know, indirect evidence. So I believe that you could observe fractional. In this case, you wouldn't have fractional charge because there's no charge to begin with, but there's fractional mass of a vortex, right? So you in principle can think of measure the depletion of mass when creating a vortex and comparing it with a say an integer fraction vortex with respect to a fractional vortex, so to say.
Oh, okay. Thank you.
Thank you again. So if there are no more questions from the audience, then I think we can move on to the next speaker.
Thank you.
So next speaker is Hui Liu. Please, Hui, take command of the share your screen and okay.
Okay, can you see my screen?
Yes.
Okay. My talk is anomalous levitation and annihilation in flocky topological insulators. This work was done with Kazama in FW Dresden and Janos in Wegener Institute. This is the outline. I will talk about topological phases, the levitation and pair annihilation in two-dimensional topological systems. Then I will introduce this process into our flocky topological system. And here we found the anomalous levitation and pair annihilation. Last, I will give a concrete example for this process, the flocky chain insulators. Okay, for two-dimensional topological system, it can be divided into two parts. The first part is the insulating bulk states, which means the electrons are localized in a certain region which do not contribute to conductance. The second part is the edge conducting channel, which means the electrons can move along this edge conducting channel and give us a quantized conductance. Okay. So it means that in its band structure, we would get a pair of chiral edge states. This gives a non-trivial topological invariance to these bands. So for this case, the topological invariant of these bands is chain number, which equal to +1 or -1. Now, when we introduce the disorder into this system, this non-trivial band would be split into two parts. The first part in the margin of the band is corresponds to the localized states, which do not contribute to conductance. The second part in the middle of the band is for the extended states. These extended states carrying inherent non-zero topological invariance and contribute to conductance. Now, when the disorder strength is increased, these two extended states carrying opposite topological invariance move towards each other in energy. In this process, the topological gap would become smaller and smaller and disappeared when these two extended states meet and annihilate at zero energy. After R, this system would become to be topologically trivial Anderson insulators. This is how Anderson localization happens in two-dimensional topological insulators. Now we introduce this process to the flocky topological system. For the flocky topological phases, its time periodical driving system is dominated by the flocky operator. Then instead of the eigenvalue for the static system, we would get a flocky operator. The flocky operator gives us a quasi-energy, which is period. So it gives us a fundamental domain at minus pi quad energy and pi quad energy. So in the Floki system, we would have two different kinds of gaps, one at 0 quad energy, one at pi quad energy. For this figure, the 0 quad energy gap is topological non-trivial because it holds a pair of chiral edge states, but the pi quad energy gap is trivial. So in the Floki system, there should be two different kinds of levitation and polarization. One happens at 0 quad energy, which annihilate all the topological states, which give us a trivial Anderson insulators. So if the levitation and polarization happens at pi quad energy, it will give us an anomalous levitation and polarization because this topological state remains here. So the system still be a non-trivial case. This anomalous process can be described by this figure. When the disorder is increased, these two extended states carrying up the topological invariance move towards at pi quad energy. So in this process, the topological non-trivial gap at 0 quad energy will become larger and larger and expands in the 4 quad energy spectrum, which give us anomalous Floki-Anderson insulators. So even in the maximum disorder strength in the Floki system, we will still get a topological non-trivial phase. Okay, so to show this process, we give a concrete example, the kicked chain insulators. The time-dependent Hamiltonian have two parts. The static part, H0, it is composed of the nearest hoping and the next nearest hoping. Along the arrow line in the left panel this represents the nearest hoping along the arrow line. It will give us along the arrow line direction. The nearest hoping strength would pick up a phase factor if it I pi over 4. For the next nearest hoping, we have two funds. Along the dashed line, the next nearest hoping strength would be V, but along the dotted line, the next nearest hoping is minus V. So the second part of the time-dependent Hamiltonian is the on-site potential kicks. So we can write the Floki operator. It also has two funds. The first part is the evolution operator of the static system. The second part represents the on-site potential kicks. The W means the disorder strength. So first we consider the clean system, which means the W equal to 0. So in this case, the quasi energy is time independent, but the phase epsilon times T is time dependent. So when we increase T, the positive band will shift to pi quad energy and the negative band will shift to minus pi quad energy. When they reach the fundamental domain of the Floki topological system, then the positive band will shift from pi to minus pi quad energy, but the negative band will shift from minus pi to pi quad energy, just like a band folding. In this process, we do not change any physical properties. The chain number of each band is invariant. It still be +1 or -1. But in this process, the band center of the positive band or negative band has changed, which shift in the quad energy spectrum. And in this process, we have many band close and reopen process. So we would get more and more edge states. Like in the figure A, we only have one edge state, but in figure B, we have 3 edge states. Now we switch on disorder, then we would observe both type levitation and polarization. Okay. When we let me switch on disorder. So when T is small, we would observe the normal levitation and polarization happens at 0 quad energy. So there is a phase transition at zero quasi energy. These four figures are the first diagram of transmission. We will see at zero quasi energy in open boundary condition, the transmission changed from 1 to 0, which means the topological gap at zero quasi energy disappeared. So this is a single nature of the levitational polarization happens at zero quasi energy. So the two extended states move towards at zero quasi energy and annihilate. So this system will become so topologically trivial Anderson insulators. As a double check, we can see that at pi quasi energy, the transmission will always be 0. So there's no topological non-trivial states in this system. So it gives us a trivial Anderson insulators. But if we increase in T, for example, T equal to 0.2, we would observe the anomalous process. For this process, the topological gap at zero quasi energy doesn't disappear. So the transmission at zero quasi energy would always be 1, even in the maximum disorder. And there is also a phase transition at pi quasi energy, but this phase transition leads the conductance from 0 to 1. So which means the topological gap at zero quasi energy will become larger and larger and expands in the fourth quasi energy spectrum, which give a non-zero quantity conductance to pi quasi energy. So this is so there is an anomalous process for at T equal to 0.2, which give us anomalous Floquet Anderson insulators that which is that in the four quasi energy spectrum, there is always a quantist transmission here. The left panel is for the case of 1 edge states. The right panel is for the case of 2 edge states. Okay, so far we have found two kinds of levitational polarization in this system, which happens either at zero quasi energy or at pi quasi energy. So it would found a competition between the zero quasi energy gap size and the pi quasi energy gap size. So it can be imagined like that. If the zero quasi energy gap size is smaller, so it is easier to shift these two extended states move towards at zero quasi energy. So this process will give us a trivial Anderson insulators. But if the pi quasi energy gap size is smaller, so this system would like to happen levitation and polarization and at pi quasi energy, which give us anomalous Floquet topological insulators, anomalous Floquet Anderson insulators. So which means this system depends on the Kleene system, the evolution operator of the Kleene system. So in these two figures, the dashed line corresponds to a criterion where the zero quasi energy gap size is equal to the pi quasi energy gap size. So here we give just a simple ruler to predict where to happen these two kinds of levitation and polarization. So in summary, we have found two kinds of levitation and polarization in the Floquet system. One is normal process give us trivial Anderson insulators. Another one is the anomalous process, which give us anomalous Floquet Anderson insulators, which means the large disorder strength will not destroy the topological states, but give us anomalous Floquet Anderson insulators, which have quantity transmission in the four quasi energy spectrum. At last, the periodical kick is much easier than the multiple step periodical quintion schemes. So we provide a simple way to make an anomalous Floquet Anderson insulators in experiments. That's all. Thank you for your attention.
Okay, thank you for the nice talk. Are there any questions from the audience? If there are, please do write it in the chat window. So I have a question. Actually, I have basically two. I have a technical question and I have a more conceptual question. The first is, how did you calculate the transmission in your system?
Calculate the transmission use
or the
scattering matrix for the Floquet topological system. It's a friction scattering process in this two-dimensional sample. So the wear modes in this lattice are dominated by the flow operator. Then when the flow operator leads the wear modes reach these two boundary of the system, then we get out modes, and we get the out modes. Then we can write a scattering matrix for this process. Then we can calculate the transmission from the Landau-Bartinger formula.
Mm-hmm. Thank you. And the other is that when you have investigated the kick chair insulator, so in some sense, this is a generalization of the chair insulator, and I was wondering whether are there any generalizations of Z2 insulators in driven systems which you can investigate in a similar way? Can you comment on that, or can you see some ways to what difference would be seen there?
I don't understand your question.
So I mean, if you would not have looked at driven systems, I mean, in driven systems, you investigate with the Floquet procedure, and in particularly here you have looked at a chain insulator which was driven with the kicks. But so I was wondering if your template system would have been not a chain insulator but a time divisor invariant insulator, so Z2 insulator, whether there could be something similar things happening, or whether the driving would somehow, can you envisage a driving which would preserve something of the nature of the time divisor invariant insulator?
For this levitation and parallelization process, we need to band have non-trivial chain numbers. That's how the levitation and parallelization happens for chain insulators. But I don't know if this system becomes a time reversal symmetry system. So I don't know for this new system which kinds of Anderson localization happens.
Mm-hmm. Okay, thank you. So if there are no more questions from the audience, then thanks again. And let's change the speaker to the next speaker, who is going to be Rafael Molina.
Hello, everybody.
Hello. Please, Rafael, can you share your screen? And I can make you.
So, first of all, good morning, everybody. Thank you for being here. Also, I would like to thank the organizers for the effort in putting together this great online conference. It has been a very good experience for me, and it has been difficult circumstances, but I think it has been a success so far. And also, of course, I would like to thank the organizers of the colloquium for giving me the opportunity of presenting our work. And this would be also a talk about topological semimetals. And in particular, we will be talking about the Landau levels and the Hall effect in topological semimetals, not only in the most famous Weil and Dirac semimetals, but also in nodal line semimetals, if I have time. And this has been a collaboration between Enrique Benito, José González, and myself, that we are part of the Condensed Matter Theory group in the Instituto de Estructura de la Materia in Madrid. And in fact, this has been most of the things I will speak about are the thesis work of Enrique. There have been a lot of excellent talks about topological semimetals in this colloquium yesterday. So, well, I think I don't have to introduce them too much, but I will introduce a little bit the model because I will use just a minimal two-band model for a Weil semimetal, and in fact my talk will I will be giving very simple ideas and very simple things. I think it's a very simple talk. And it's a three-dimensional model, and it's anisotropic. Because this chi-set is only here in the diagonal part, the chi-set squared, and here only you have chi-x and chi-y. And of course, you can solve this model and you find this band structure. And if M0 and M1 have the same sign, you have this inversion, mass inversion, band inversion, and these two band crossings with the binodes at this position here. And we can look for decaying surface states, and that will be the famous Fermi arcs that will be living in just a finite domain in momentum space. They will appear if we have just a surface, but they will not appear in every surface. For example, here with this Hamiltonian, they will not appear if we have a finite width in the z direction. They will be flat in the kz direction, and they will disperse linearly with ky. And this minimal model is based on a model proposed to describe the low energy excitations of one of the first materials that was discovered in this family, sodium bismuthide. That is a Dirac semi-metal, and in fact, in the Hamiltonian, you have essentially two copies of the Hamiltonian that I showed before, with the difference that we have some dispersion part that depends on goes with the unit matrix. And there have been experiments, ARPES experiments, that have shown that for low energy, this model correctly describes the band structure. The parameters essentially are given by fits to DFT calculations in this case. There have been many experiments in the last years showing this kind of behavior for bisemimetals or Dirac semi-metals for many different materials. I won't go too much into detail, but there are also another family of materials or another type of materials in this family, the nodal line semi-metals, that in fact can be described by this, some of them can be described by similar Hamiltonians, where we have taken out the part that goes linearly with ky, and they show a nodal loop. The binodes form a continuous curve in the previous zone. And there is a tremendous amount of experimental work studying topological semimetals in magnetic fields. Certainly, the interesting properties of topological semimetals under magnetic and electric fields are one of their signatures, like the famous chiral anomaly. But the things that concern us most in this talk is that these materials have raised the possibility of measuring a true three-dimensional quantum Hall effect. Maybe this is one of the dreams in condensed matter for many years, but most of the measurements of quantum Hall effect in three-dimensional materials could be interpreted as just a stack of two-dimensional independent quantum Hall effects. So here things may be different, and we can find a really three-dimensional quantum Hall effect. There have been different experiments, but the one I like most is perhaps this one with cadmium arsenide, where they have a bar of quantum Hall bar and an experiment with different contacts. But this bar is not really a bar, but a wedge. So in one of the dimensions along this direction, the width of the bar changes linearly here. And this was really to prove that we have a really three-dimensional quantum Hall effect where this width plays a role. And in fact, the way they interpret these experiments is via a new kind of orbit, or a new kind of cyclotron orbit in these materials that they call the Weil orbit. The theory, I think the first theory paper is this one. And here you have, in a normal 2D material, this will be the cyclotron orbits. Here you will have an orbit in the two surfaces where the fermions live, but they are connected by the bulk. So the cyclotron motion will be this part in the low surface and this other red part in the upper surface, and connected by the bulk. And to prove this, so they have in reality like 4 terminal experiments, but the terminals are in different positions with different widths, and they find different signatures of the quantization of the conductor, the resistance here, depending on the width. So we wanted so these are really beautiful experiments, but are difficult and delicate, and we wanted to understand this a bit better. And in these experiments, they have really a semi-classical interpretation. We wanted to understand if this could be understood from the simple models in a quantum mechanical way, and hope that results could be useful in the search for reproducing these results with other materials, for example. And first, I want to study the bulk Landau levels in Weil semi-metals. And of course, as these are not isotropic, you can try different geometries, and the Landau levels could be different depending on whether the magnetic field is pointing in one direction or the other. So if the magnetic field is parallel to the line joining the nodes, I mean, the line, of course, is in the momentum space. If the line joining the nodes is in the KZ direction, and the magnetic field is pointing in the Z direction, we can use the Landau gauge and find, through minimal coupling, try to understand what are the Landau levels of this minimal model. And to diagonalize this problem, we can use the basis of a harmonic oscillator, in the X-plane, centered at minus chi y over the magnetic field, and with this frequency. So this is a parameter of that depends on the material, and this is the magnetic. So we can define this kind of creation and destruction operators, and this will be the Hamiltonian that will appear. It seems complicated, but in fact it can be solved exactly as was done in this paper. Well, first of all, I want to point that the states that you will find will be fully degenerate in KY. So you will have a huge Landau degeneracy, and you can solve analytically the states. This will be the energy of the zero Landau mode that will have this structure. So it will only live in the lower spinor, and the other Landau modes, the wave function will have this structure. And you can show, you can find here a figure with a plot with the results for the energy, and depending on the chirality of the Weil node, the Landau zero Landau level will point down or up. So in a Dirac, for example, in a Dirac semi-metal, you will have both. And if you only have one Weil node, the particle Hall symmetry will be broken by this zero Landau level. But the Landau levels keep some chirality in this direction. If we, instead of the parallel direction, we put the magnetic field in the perpendicular direction and try to find bulk Landau levels, we find we can do a similar transformation to creation and destruction operators, and this will be the bulk Hamiltonian. And here the chirality is mixed. This cannot be solved analytically, or at least I don't know how, but it can be solved numerically, and you find the destruction of the Weil nodes. And this has been shown experimentally. Now, instead of solving the states in the bulk, we will solve the states in a slab configuration in this direction, that the last direction, with the magnetic field perpendicular to the line of nodes. And of course, we can substitute the K set by an operator, and we will have a finite dimension in the set case. And plotting the results of this numerical calculation as a function of the magnetic field for two different widths, we find that the surface states that in this case live in these two surfaces depend on the magnetic field. They are zero modes up to, for the longest widths, they are zero modes up to some particular value of the magnetic field where they start to separate. So this will be the states coming from the surface, and this will be the states coming from the bulk. At this particular value of the magnetic field, the surface and the bulk states start to hybridize. Here I show the wave functions, and for example, for 30 Teslas, you see a mix of bulk states and surface states in the density, and this will be the quantum mechanical equivalent of Weil orbits. And now, in fact, what we find is that there are two regimes, two parametric regimes, depending on the parameters of the Hamiltonian. We call them inversion regime and Weil cone regime. Here, instead of a slab, we have a bar with two finite directions. In the inversion regime, where you have this much bigger than the quadratic terms must be much bigger than the linear terms, there is a whole bunch of states of very mixed states that the bulk is just mixing in the whole and the particle part of the bulk is mixing. And while in the Weil cone regime, the whole and the particle part are very well separated. If we plot the wave functions here, there you will have a lot of nodes in this inversion regime, while in the Weil cone regime, you have very nice wave functions that in this part that is starting to disperse are localized at the surface. So if we want to find the whole conductance here, there you will have contributions to the current that really you cannot expect to find quantized conductance, because you will have contributions up, down, with different signs, very complex situation, while in the Weil cone regime, you will have a very nice quantized conductance due to this nice behavior. In the other geometry, you have very similar situation, although the states cannot live mostly in the bulk. And as a conclusion, well, we have a well-ordered sequence of Landau levels in thin films of white semi-metals, but only in some parametric regimes, where we have well-separated electron and hole-like levels. This seems to be relevant experimentally for many materials, but in fact, the parameters are quite close to the change of regime. So deviations may prevent the observation of conductance quantization. And, as we increase the strong magnetic field, we increase the magnetic field, we can move from the to the wide cone, what we call the wide cone. That's what I wanted to tell you about wide semi-metals. I don't have time to go to the other work on nodal line semi-metal, but that's fine. And thank you.
Thank you, Rafael, for the nice talk. So I think there are a couple of people in the audience who have done some recent work related to this field. So I really encourage now someone from the audience as well to contribute. I don't know. So actually we have just a bit of time because we were a bit economical with it. I would be also interested into seeing what conclusions could you do related to the nodal lines, actually.
Well, in the nodal lines, well, I can show you. So, in the nodal lines, in fact, we have very so in the wide semi-metals, you have seen that this is very messy, but in the nodal lines, due to the symmetry of the nodal of the nodal line that has this whole line of nodes, we can really separate between a 2D quantum surface Hall effect and a 3D quantum surface Hall effect, depending on whether the magnetic field is perpendicular to this nodal line, or in the case of 3D, parallel to the nodal line. Mm-hmm. And in the case of 2D quantum surface Hall effect, we can come up with a topological index that counts the number of states. And we do this by changing to the complex plane, because the whole the Landau states from the surface can be transformed into exceptional points, and then we can use tools from complex calculus to find this formula for this topological index. And really here we expect a nice quantization of the conductance up to very large numbers of n. Mm-hmm. So it will be much easier if you have a really good nodal line in a slab, a clean sample, it will be much easier to see.
So this requires the nodal line to be a loop, or so a nice
we
loop?
have used a loop. I don't think it requires, it's a requirement, but in our models it was always a loop. Mm-hmm. I don't think this is an important requirement.
Okay, thank you.
So I have a small question concerning the same topic. So at the end of the day here, in the case of the nodal line, you have to resort on numerics, right? Because it's the situation, if the magnetic field is parallel or perpendicular to the nodal line, could be quite different and quite messy, right?
Yes, but but the numerics show that, for example, well, this is the numerics for this geometry. These are the numerics for this other geometry, and in both cases you see a very large degeneracy of the zero mode. That it doesn't happen in the wide semi-metal.
For instance, something we did with Laszlo was to make a semi-classical analysis.
Another question. Yeah, here in the 2D quantum surface, at least for the zero mode, you can do analytics. Not for all the quantum Hall, not for all the quantum Hall states for large indices, but for the zero mode, you can do analytics. Yeah. But please go ahead.
No, sorry. I was saying that working with Laszlo, we studied something magnetotransport in nodal lines in the semi-classical at the semi-classical level, and we found that it's extremely difficult to disentangle trivial and topological orbits. So I'm wondering if how clean would be the signal of this Hall effect if we, in these nice pictures, you have both trivial orbits and topological orbits.
Yeah, well, in fact, we did the approach for both works. In fact, is quite different because here we didn't try to establish a connection between the semi-classical orbits and the quantum orbits that we found. It was more an analysis based on this complex, extending the region zone in the complex plane and try to find this, to count the number of states at 0 modes. So I'm not sure, but maybe we can try to understand better the connection.
Yeah, so I mean, you made a really good job just putting surfaces and boundary conditions. That this is, I mean, this is huge work. So thank you for the answer.
Thank you.
Okay, thank you, Rafa again. And I think we can now move on. I think it's Artur Beirat. And please, Artur, can you take over the screen and
okay,
switch
is it
on
working?
Yes.
Perfect.
Okay.
Thank you very much.
You have 20 minutes.
So, good morning, everyone. My name is Artur Beirat. I'm a PhD student at the IFW in Dresden. And today I will tell you about our recent study of trigonal platinum bismuth 2, a van der Waals material in which we found superconductivity. So platinum bismuth 2 is a very interesting material in general. It is perhaps best known for the presence of an extremely large magnetic resistance in its pyrite structure, up to about 10 million% at 33 Tesla. The hexagonal structure also shows a giant linear magnetic resistance, which may be related to the presence of direct surface states at the edges of the Brillouin zone. The compound that we studied was the trigonal one. As I said, it is a van der Waals layered material. Each layer is made of 2 inequivalent planes of bismuth with 1 plane of platinum in the middle. So the compound shows a high spin-orbit coupling as well as an inversion symmetry breaking. These last 2 points give rise to a giant 3-dimensional Rashba-like spin splitting, as has been recently observed. And some theoretical calculations have shown the existence of a triply degenerate point in the band structure at about 300 millieV above the Fermi energy. So this is quite high for us to be able to observe using transport measurements. But nonetheless, this should show you that trigonal platinum bismuth 2 is an interesting material on a topological point of view. And indeed, when we made some band structure calculations in our institute using density functional theory, we found the existence of 12 symmetry-related Veil nodes here at about 48 millieV above Fermi energy. As you can see here, though, the density of states does not vanish at the level of the Veil nodes, and that is due to the presence of a number of other bands crossing the Fermi energy. So we wanted to investigate these materials using transport measurements. So the first thing that we did was to simply contact bulk crystals of trigonal platinum bismuth 2 and cool them down to about liquid helium temperatures. Doing this, we measured triple R of about 130, which is a sign of good crystalline quality. And then we looked at the magnetic resistance in our sample. So here you can see the magnetic resistance versus magnetic field for a range of tilting angles of a field, 0 corresponding to a perpendicular field and 90 degrees to a planar field. For perpendicular fields, we found a bit more than 2000% magnetic resistance at 15 Tesla, which puts this sample into the range of giant magnetic resistances. But you can see that the maximum of magnetic resistance is not reached for perpendicular fields, as is usual, but for a slightly tilted away field by about 20 degrees. So this has already been observed previously with quite close values in terms of the angles. And if we plot the maxima of magnetic resistances at each tilting angle at 15 Tesla, what we find is this graph, which shows that the perpendicular resistance, the perpendicular direction is actually a minimum of magneto resistance, local minimum, that is surrounded by two maxima, so at plus or minus about 20 degrees. Then we cool down our samples even further using a dilution fridge. And this is the measurements that we got. So we had the nice surprise of finding out trigonal platinum bismuth is actually a superconductor at low temperatures. If I zoom in on this, you can see the superconducting transition happening at around 600 millikelvin. So here I define the critical temperature as being that for which the resistance reaches half of its normal value, and I will use this definition throughout this talk. If we apply a magnetic field to our sample, we also see that the zero resistance state is smoothly broken with increasing fields, and we have a critical field of about 60 millitesla when defined in the same way as previously. If we want to study the superconductivity in this sample, we can repeat this measurement, which was done at our base temperature, that is about 100 millikelvin. We can repeat it at different temperatures and look at the dependency of the critical field versus temperature. So this is the result of this study. So as you can see, the critical field behaves very linearly with temperature down to temperatures quite far away from the critical temperature. This is expected from the Ginzburg-Landau theory at 3 dimensions, from which we can extract a value, a zero temperature value of the superconducting coherence length of about 54 nanometers. This is quite interesting because, as I said before, trigonal platinum bismuth 2 is a van der Waals material, so it is possible to exfoliate it mechanically using Scotch tape down to such thicknesses. And this way, we may be able to study the behavior of a superconductivity when it is constricted to 2 dimensions. So in order to do this, as I said, we mechanically exfoliated our crystals on silicon dioxide substrates. So here you can see the platinum bismuth 2 flake that, which results I'm going to show in the rest of this talk. It is about 60 nanometers thick and was contacted using standard e-beam lithography procedures. It shows a triple R of 9, which is lower than for bulk structures, but this is expected since this is an exfoliated structure. Nonetheless, it still shows a nice superconducting transition happening at around 370 millikelvin. When we applied a magnetic field to our sample, the first thing we noticed was that we have a very different response whether we apply a perpendicular field in blue or a planar field in red, with a much lower critical field when the field is perpendicular to the sample. This is actually understandable on a simply as a geometrical effect, since our sample is much wider than it is thick. So it is going to be more difficult to expel the field around the sample if the field is applied perpendicularly. We also did some differential resistance measurements, so dV over dI. So here shown versus DC current. At low current, we have the typical superconducting state of zero resistance. At high current, we find a normal resistance state. And in the middle, we have these differential resistance peaks. So this measurement was made at base temperature, but we also made it for a range of temperatures up to temperatures above the critical temperature. All the curves are shifted vertically for visibility. And you can see that with increasing temperatures, the hallmarks of superconductivity, that is the zero resistance state, as well as these differential resistance peaks, smoothly vanish and disappear at higher temperatures. So this is a good proof that we have superconductivity in our exfoliated structures. Now, since we have a very thin structure with a thickness very close to the superconducting coherence length in bulk samples, we would like to investigate the dimensionality of a superconductivity in this sample. So for this, we look at the behavior of a critical field versus tilting angle of a field. Once again, 90 degrees being for 0 degrees for perpendicular field, 90 degrees for planar field. And so we expect to have a maximum of critical field for 90 degrees for the planar field. What we find out actually is that we have a maximum at 91 degrees. This 1 degree offset is actually simply due to a misalignment of a sample inside our measurement apparatus, since the sample is simply plugged in by hand in the measurement device. So if we take that misalignment into account, we can fit our data using either the two-dimensional TINCAM model or the three-dimensional Ginzburg-Landau theory, respectively in red and blue. And as you can see, the two-dimensional model in red fits our data much closer. So this is a good indication that we have two-dimensional superconductivity in our sample. If we want to study this further, we can look at the behavior of a critical field versus temperature this time. So here for the perpendicular critical field, we have a very linear behavior down to very low temperatures. This is expected for both the three-dimensional and the two-dimensional Ginzburg-Landau theories. But the three-dimensional Ginzburg-Landau theory expects also a linear behavior for the planar field. And this is not what we observed. We observed a dependency in square root for the planar critical field, which is expected based on the Ginzburg-Landau theory for two-dimensional superconductors. So from these fits, once we take the misalignment into account, we can extract a planar coherence length of about 83 nanometers at 0 temperature, which is of the same order as what we had in bulk samples. One interesting effect that we can expect to see in two-dimensional superconductors is the so-called Berezinski-Kosterlitz-Thouless transition. So as you may know, at 2 dimensions, there is no long-range order possible, according to the Mermin-Wagner theorem. So that means that for a superconductor, even below the BCS critical temperature, there will exist some vortices and anti-vortices that will be unbound and will drift away when a current is applied. They will drift in opposite directions. This will cause phase fluctuation, which will result in a non-zero resistance, even below the critical temperature. But there is the possibility of a quasi-long-range order, and that is the essence of a BKT transition. So below another critical temperature, the vortices and anti-vortices are expected to pair up and bind together, which means that these pairs will no longer drift when a current is applied, and this will result in a transition to a zero resistance phase below this BKT temperature. The two-dimensional superconductivity is unfortunately very sensitive to this order, and the BKT transition as well. It has usually only been observed in very thin films. The thickest film which we could find displaying such a transition in the literature was an NBN film of only 12 nanometers thick. So our sample is quite thicker than this, but we still looked at whether we could see some signs of a BKT transition. So the easiest thing to do is to look at the current versus potential profiles plotted in a log-log graph. So at high temperature, we expect to see a linear behavior, simply the ohmic regime. At very low temperature, we expect to see a more a power law as we have superconductivity. And according to the BKT model, if we have a BKT transition, at the BKT temperature, we should find a power law of order 3, exactly. So this is what we find at around 310 millikelvin, but it is maybe not very visible in this plot. So what we can do for the better visibility is to simply take the logarithm derivative of the potential. This way, we're directly looking actually at the exponent of a power law, and we can see more clearly that it is at around 310 millikelvin that the power law of order 3 is reached. These IV curves are obtained obviously applying a DC current. So these measurements are made out of equilibrium. Maybe to have a better proof of having a BKT transition, we can look at equilibrium measurements. So these were made, so this proof is from looking at the resistance versus temperature profile once again. So according to the BKT theory, we expect to have an abrupt transition at zero resistance below the BKT temperature. So this is a fit using the Halperin-Nelson homogeneous model. As you can see, it is completely unable to account for the tail in our data, and that is actually because the BKT model, in a sense, is an homogeneous one. But according to this paper, we actually have to take inhomogeneities into account in real samples. So we can think of inhomogeneities as if we had some local transitions happening at different temperatures at different places in our sample. To model this, we can consider that we have a Gaussian, for instance, distribution of BKT temperatures and integrate the response over this entire distribution. This is what we did here in blue. You can see that we have a very good agreement with our data, and this for only a quite minor spread of transition temperatures. So this is a good proof that we have an BKT transition happening in our sample, even though we have quite fixed samples, so we're very far away from a single or even a few layer limit. So to summarize our results, we have calculated that trigonal platinum bismuth 2 is a Weyl semi-metal with Weyl nodes quite close to the Fermi energy. We have found superconductivity as in bulk sample as well as in exfoliated nanostructures. We showed that we could reach the two-dimensional superconductivity limits in exfoliated structures, and even that we saw signs of a BKT transition, an inhomogeneous BKT transition, even in quite thick nanostructures. So with this, I come to the end of my talk. I would like to thank all the people that made this study possible. And of course, I would like to thank you for your attention.
Okay, thank you, Arthur. Are there any questions from the audience? Please feel free to ask or type.
Yes, I have a question.
Okay.
Yeah, you said that you have this 2D superconductivity in thick samples. Yes. So did you try to control somehow the thickness for the samples and see how this evolves?
So we have done a study with a thicker sample, slightly thicker, few dozen nanometers thicker, and we do not see this sort of direct hallmark of 2D superconductivity. So with a very different perpendicular and planar superconductivities. We haven't been able yet to reproduce this study in thinner samples. We're currently starting the measurements. So, but this is what we expect to see for even thinner samples.
So there is something special for this this particular thickness, or not?
I think this sample is quite at the frontier of thickness. That our thicker sample is not displaying 2D superconductivity. I am not sure if we expect something drastically different for thinner samples. So I think thinner samples should also display this sort of behavior, perhaps even more exacerbated.
So it's a technical point, right? Yeah.
Yes. Also, platinum bismuth 2 is the trigonal platinum bismuth 2 is actually quite soft material with weak in plane strength. So it tends to break in tiny flakes rather than exfoliate very well. So this is why it has taken us some time to study thinner structures in this.
Okay, thank you. I think that also answers the question that was posed in the chat by Daniel Munoz, who asked about the limitation about fabricating samples. So
yes, I wasn't looking at the chat. So yes, the main limitation of fabricating these devices is, so of course we're doing exfoliation, so we don't have a scalable fabrication process for making many devices. Also, platinum bismuth 2 is very metallic, as you saw from the band structure. So that means that even on silicon dioxide substrates, we don't have a good color contrast for directly seeing with optical microscope the thickness of our samples. So it is actually quite difficult to find thin structures, coupled to the fact that it's actually difficult to exfoliate thin structures.
Okay, are there any more questions? Okay, Daniel is also satisfied, I think. Okay, so if there are no more questions, I think we can move on to the last talk of this session. So Sarah Pignon, can you, Sarah, please share your screen?
Yeah, hi. Okay, I think that should. Can you see my screen?
Yes, I think you can start. You have 20 minutes.
Okay, so hello everyone. I'm going to talk to you about quasi-particle interference in valence semimetals, and I will talk about a method to obtain them using surface Green's functions. So by now you have seen a lot of introductions on valence semimetals, but I'll just mention again one of the few points that I will need in this presentation. So valence semimetal is a topological system where in the bulk, the energy spectrum is linear at low energy, and the points where the bands cross are called the valence nodes. Now, if we look at the surface of a valence semimetals, we have surface states at 0 energy, and in the surface Brillouin zone, these looks like lines. So these are called Fermi arcs. And these arcs end at points which correspond to the valence nodes that are projected on the corresponding surface. So the question we want to ask in this presentation is, how do these Fermi arcs scatter? So if we have impurities on the surface, this will cause scattering, and this is seen as a modulation in the local density of states. Now, if we go to K-space, we see what we call quasi-particle interference patterns. So these are two examples of QPI patterns that can be obtained experimentally. So what you need to do is to take the Fourier transform of STS maps. So here we have two examples of two different valence semimetals. Here on the left, we have a QPI for TAAS, and here on the right, we have one for MOT2. So theoretically, to approximate the QPI pattern, there are two common tools that are called JDOS and SSP, which are often obtained using a DFT calculation beforehand. So the first one, the joint density of states, is computed using this formula. So basically, we do another correlation of the surface spectral function at a given energy. Physically, what this means is that we consider that each surface state scatters with all of the other existing surface states that have the same energy. So in the equation, this is seen as taking the surface spectral function at a momentum k and energy E, and then the surface spectral function at another momentum k plus q, and then we integrate over k. So we take all of the existing surface states at a certain energy E. Now, the SSP is a correction to the JDOS, actually. So it's called the spin-dependent scattering probability. And so this is the equation that we have for a pure state. So it's a bit different for a mixed state. And so comparing to the JDOS, we add this new parameter alpha, which is a spin-dependent weight. So this is one way of defining alpha. So for example, we can define it like this, where here S of k represents the spin of the state at momentum k. So in this case, if, for example, the spin of the state at momentum k and the one at momentum k plus q are anti-aligned, then alpha equals 0 and the SSP is equal to 0. So this means that we have no scattering between states that have opposite spins. And conversely, if the spins are aligned, then alpha is maximal and we have full scattering. So now I'm going to talk to you about another method that we use to compute this QPI, which is based on Green's function, and it is exact for a localized impurity. So this is the formula on how to compute the Green's function of a system when we have an impurity. So if we start with an unperturbed system, which is described by this unperturbed Green's function G0, then the T matrix T here is representing the action of the impurity, the scattering that is caused and that acts on the unperturbed system. So this T matrix can be computed very easily using such a formula if we have a localized impurity. So it depends on the unperturbed Green's function G0 here, and then on V, which is the potential which represents the impurity. So what we want to compute is the modulation in the local density of states. So we call this delta rho, and this in real space is proportional to the imaginary part of G0 T G0, which is the perturbed part of the Green's function. And if we do a Fourier transform of that, we can obtain delta rho in K space. And we have a formula that looks like this. So here there's a little mistake. This should be Q instead of K, but anyway. So here we get such a formula. So again, we can compute delta rho easily from just G0 and T. And so in our case, we want to study a Waal semi-metal, and we want to study the scattering of the surface states. So the G0 we consider here is actually the surface Green's function, the Green's function of the surface of the Waal semi-metal. So this is the entity we need to compute first, and it's not necessarily easy, but we found a method to compute this. So this is just going to be a very quick explanation of how to get this, but if you want more information, Christina Benner made a pre-recorded talk for this conference where you can find more information about this. So let's imagine first that we have a 3D infinite system, and we add to it an infinite plane impurity. So this is represented by this black square here. Imagine it's infinite. So if our impurity is very strong, then effectively our system will be cut into two semi-infinite parts, the blue blocks here, and then surfaces will appear on these blocks. So these surfaces are parallel to the plane impurity. Now, if I describe my original system with the block Hamiltonian H, I can then obtain the unperturbed Green's function which corresponds to it. And then from the equation I showed you earlier, I can compute the Green's function for the whole system. So now my system plus the impurity. And again, we have a T matrix where this time V corresponds to the plane impurity we have added. And so to get the surface Green's function, all I need to do is to set the Green's function at XS, so the position of one of these created surfaces. So to do that, since I compute first G in K space, I must do a partial Fourier transform in one direction, the direction which is perpendicular to the surfaces. So this, now we have our surface Green's function. Okay. Now I'm going to give you an example of how we applied this method. So we took a model that was given in a paper by Cortes et al. So this is the Hamiltonian that they propose. So this is one for a Waal semi-metal where we have two kinds of degrees of freedom. We have spin, which is described by the Pauli matrices sigma, and then we have an orbital degree of freedom, which is described by the Pauli matrices tau. So the first thing we do is we apply our method and we compute the surface Green's function for this system. And then we can obtain the surface spectral function at zero energy. So this is something that is proportional to the imaginary part of our GS. And we obtain something like this. So here you can see the Fermi arcs appearing. So this system has 4 Waal nodes and 2 Fermi arcs. So one thing we did when looking at this system was to look at the spin polarization of the Fermi arcs. And we saw that the Fermi arcs have opposite spin polarization. Now this is important because in one of our previous papers, we showed that scattering between states that have opposite spins can only occur if we have magnetic impurities, and then they can only be seen in experiments if we have spin polarized STM. So here in our case, we expect that there will be no inter-arc scattering, because if we have a scalar impurity, that is, and this is what is considered in particular by Curtis in their paper. So these are the results for the QPI. So on the left, we have what is obtained by Curtis et al. Using SSP, and this is how what we obtained using our method. So as you can see, for one, the intra-arc scattering looks different. So this is the pattern in the middle of the figure. And also we find no inter-arc scattering. So this corresponds to the results we found on the spin polarization of the Fermi arcs. We expected that. But Curtis et al. Still obtained something, some inter-arc scattering shape, which looks like a wing here. Now, this model that I presented by Curtis is supposed to model certain kinds of valse semimetals, including MOTE2. So this is the picture I showed you earlier of a QPI obtained experimentally on MOTE2. And as you can see in the QPI pattern, they do observe some inter-arc scattering, which looks like wings. Now, the thing is, this experiment was done with a non-spin polarized STM. And as I said earlier, this means that we should not be able to see scattering between states that have opposite spins. So what we concluded from this study was that probably the model that is proposed by Curtis et al. Does not represent the spin structure of valse semimetals such as MOTE2 correctly, and the Fermi arcs that you should obtain should actually not have opposite spin polarization. We also studied another model, this one proposed in this paper. Here we again have two Fermi arcs, but this time they're a little bit displaced. And this is what they obtained for the QPI pattern. This time they used JDOS, and this is what we obtained. So again, we did we looked again at the spin structure, and we saw this time that the spin polarization of the Fermi arcs are nearly opposite. And so we expected to have some weak inter-arc scattering, and this is what we observe here. So we see some weak shape here. And that's also something that is obtained in the JDOS by Lowe et al., except that here so they don't set the color bar, but the intensity of the inter-arc shape is basically the same as the one for the intra-arc scattering. Okay, so to conclude, I'm just gonna say a few more words about this technique that we have to compute the Green's function. So this is a tool that we use to study edge and surface states in general, and we have applied it in particular to other systems, such as acinus junctions, topological superconductors, and 2D topological insulators. And as I showed, this method can also allow us to compute the QPI. And the results that we find, at least for valse semimetals, differ greatly from what can be obtained from JDOS and SSP, the usual theoretical tools that are used to compute the QPI. In some cases, we can also get analytical results for the Green's functions. So we show this in this preprint. In particular, we have this simpler valse semimetal model where we have only one Fermi arc here. And this is a plot of the surface spectral function that was obtained completely analytically. So this is just a plot of a single function as a function of momentum. And this is the QPI that we obtained from the previous analytical results. Okay, that's it. Thank you for your attention.
Thank you, Sarah. So the floor is open for discussions. So
Laszlo, I have a question.
Yes, Roberto.
Sorry, Sarah, do you have any clue why you get different results from these two other techniques?
We get different what? I'm sorry.
I mean, why you get different results when compared with these joint density of states and the...
So it is known that JDOS and SSP, so as I show in the mathematical expressions, that these are approximations of the QPI pattern. Like what you need to compute is the Fourier transform of the local density of states. And this is not what they compute. So they compute something that depends directly from the surface spectral function, and it's an approximation. So things are lost when you compute these quantities that you don't lose if you compute the Fourier transform of the LDOS directly. So in particular, some things, I guess, about the spin structure can be lost. For example, if you only take JDOS and you don't take SSP, you have no information on the spin structure because you don't consider whether the states scatter depending on their spin or not.
Yes, Alberto, is it okay?
Yeah, sorry.
So am I correct in understanding that basically your method takes the SSP one step further in incorporating all the proper matrix elements? Basically, you can think.
Well,
are there something
a bit more than that because SSP remains like more of an approximation. We compute directly the Fourier transform of the LDOS. So, I mean, in the case at least of a localized impurity, we can get results that are exact mathematically. So it's more than taking the SSP further. It's I don't know. I wouldn't.
No. I mean, can it be that the exact Green's function could be cast in such a form that you have some sort of SSP-like form for the thing what you see? So can you cast? Is there something else? So I would assume that the true local density of states, you build up your local density of states from the particles on the Fermi surface, and in principle, if you would know all the matrix elements, not just the spin part of the matrix elements, but the proper matrix elements between the states, you should recover a formula which looks like the formula for the SSP, but with an altered matrix element.
So I'm not completely sure about what you mean, but usually, so I would say that these matrix elements that you're speaking of are actually lost when you do the SSP. Like there are some that you don't consider.
Yes, that I understand, but in principle, you can just solve your Hamiltonian in each point, and you would have all the wave functions for all the states, and you could calculate depending on your scatterers and depending on your details of the potential on the surface, the actual matrix elements of the scattering states.
You mean that's what they do?
Can I say things, Alberto? Do you mind if I say something?
Yeah.
Alberto?
Yes. Please.
Can you? I mean, you unmute yourself, right?
Yes, I did.
Yeah.
No, I don't think it's possible. First of all, the energy dependence in this scattering amplitude, it doesn't work in the SSP at all. There is no energy dependence there. So in T matrix, you also have the energy dependence correctly, which here in SSP is not taken into account at all. So that's one thing which you cannot recover by an expression in matrix elements. And then more than that, I think it would be complicated to really express you have to take really the components of the Green's function, then you go back to the T matrix. I mean, it's really hard to write it in terms of the spectral function components because spectral function is already an imaginary part of something. And then if you have to write it as a product of two imaginary parts, then you miss a lot of information. So you already projected the Green's function on the spectral function when you write the SSP. So in the Green's function, you have two matrices you multiply, and then you take something at the end. Here you have the A's separately, and then you multiply them. A already was projected the spectral function on the Green's function on the spectral function.
Okay, thank you. I think that makes it a bit more clear. Okay, thank you. Are there any more questions left? Actually, we have still like 5 minutes official time left from the session, but I think there are also some other speakers from yesterday's and Wednesday's session. So I think this would be first of all an ideal place to thank everyone for joining in and contributing to our session. And I think we also really need to make a picture first before everyone leaves.
Yeah, for anyone who wants to switch on their camera, let me try to see if we can do. How many of you can switch on their cameras
Please.
now?
I think Helena, please, could you try? Alberto, you are not switched on yet.
Yeah, I did.
Okay.
Let me change the.
Olivia, can you switch on your camera?
I think I made permits.
No. At least we should get all the speakers. I think we lost our invited speaker, sadly. But I think if the others are here.
So now please smile and say cheese. So thank you very much. And I hope you enjoy, as we did, this mini colloquium. So we found very interesting results, and they were presented in a very brilliant way. So I want to thank all the speakers and all the attendants for participating in this colloquium. So it was a pity not to see you all personally here in Madrid. Hopefully, let's see if we can do in the future, in the near future, I mean.
And I think we can still have some time for further discussions. I think Joao.
Yeah, the session is scheduled to be open till 1:30 p.m. So just in case you want to discuss with any of the participants in the colloquium, I'm not sure if I was succeeding in opening the cameras, but I'm gonna try to open the participants to open the microphones by themselves. So I think now anyone can open the microphone, the speaker, and just to ask questions, I guess.
And I think that there were some questions to Joao, if people around who wanted to discuss that.
Actually, I had a question for Joao, I remember yesterday. Yeah. So Joao says like he cannot open the micro, KLD. So can you try now? No, crap.
I can.
Okay, good.
Oh, it's okay.
So my question was related to what happens.
Alberto, do we want to keep on the recording?
Okay, so let me finish the record. So thank you everyone again.
Mm-hmm.